Hey, and welcome. Ever feel like life is just one big gamble after another? Well, today, we're going to turn that feeling into a superpower. We're jumping right into the world of basic probability, not to make you luckier, but to help you think a whole lot smarter about chance. Let's get into it. Think about it, right? We do this all day, every day. We make decisions in the face of uncertainty. Should I pack an umbrella? Is this stock a good buy? We are constantly, and I mean constantly, playing the odds, even when we don't realize it. But what if we could do better than just guessing? The good news is we absolutely can. Today, we're going to build a foundational toolkit for thinking about probability, giving you a real structured way to handle all that uncertainty. Okay, so the first and most important tool in our kit is something called a probability model. Really, just think of it as a complete map of every single thing that could possibly happen in a situation, along with the chances for each of those things. And to really wrap our heads around this, we're going to use a classic example that you've probably seen before, but we're going to break it down. Let's just imagine we're rolling two normal six-sided dice. And here it is. This grid is our map. This is what we call the sample space. Each of these 36 little squares represents one unique outcome, from rolling a 1 and a 1 all the way down to a 6 and a 6. And since the dice are fair, every single one of these 36 outcomes is equally likely. That gives each one a probability of 1 in 36.
Okay, so now that we have our map, we can actually start asking some interesting questions. Let's say we want to know, what's the probability that the two dice add up to exactly 5? How do we figure that out?
Well, the process is pretty simple. First, we just look at our map and find every single combo that adds up to 5. So we've got a 1 and a 4, a 2 and a 3 and a 2, and a 4 and a 1. That's 4 successful outcomes. The last step? Just divide that number, 4, by the total number of possibilities, which is 36. And boom, there's our answer. The probability of rolling a sum of 5 is 4 out of 36, which is about an 11.1% chance. See? Our model gave us a super precise answer. No guesswork needed.
All right, tool number 2 for the kit. And this one is a fantastic shortcut. It's for figuring out the probability of something not happening. It's called the complement rule.
The logic here is actually super simple. The total probability of everything that could ever happen always adds up to 1 or 100%, right? So the chance of something not happening is just 1 minus the chance that it does happen. This little trick can save you so much work.
Let's put this to the test with something a little more delicious. So, according to Mars, this table right here is the actual probability model for the colors you'll find in a bag of M&Ms. Notice two key things. All the probabilities are between 0 and 1, and if you add them all up, they equal exactly 1. That's how you know it's a legit probability model.
So here's the question for you. You reach into a bag and pull out one M&M. What is the probability that it's not blue? Now, you could add up the probabilities for orange and green and red and yellow and brown, but trust me, there's a much faster way.
And that is where our shortcut comes in. This is the complement rule in action. Instead of adding up 5 different numbers, we can see that the probability of not getting a blue M&M is simply 1 minus the probability that you do get one. All we have to do is subtract 0.207 from 1.
And that gives us 0.793. So much faster than adding all those other numbers, right? It just shows you the power of having the right tool for the job.
Time for the third and final tool in our basic kit, the addition rule. This one helps us find the probability of one thing or another thing happening, but with one important condition. They can't both happen at the same time.
And that brings us to this key idea of mutually exclusive events. Yeah, it sounds a little technical, but the idea is dead simple. Two things are mutually exclusive if they have 0 outcomes in common. An M&M can be red, or it can be green. It can't be both. They exclude each other.
And here's the best part. When events are mutually exclusive, the OR rule is about as easy as it gets. To find the probability of picking a green or a red M&M, we literally just add their individual probabilities together. So we take the probability of green, add the probability of red, and we get our answer. Simple as that. Okay, we've built our toolkit. We've got our map, our not rule shortcut, and our OR rule. Now it's time to put them all to work in a real-world scenario, analyzing scores from the International Baccalaureate Math exam.
So this table shows us the probability model for a randomly selected student getting each possible score, from a low of 1 to a high of 7. And yep, if you check it, all those probabilities add up to 1.
Now here's the rule of the game for this exam. Any score that is a 4, a 5, a 6, or a 7 is officially considered a passing score. That's our goal.
So, that leads us to the big question. What is the probability that a randomly chosen student actually passed this exam? How can our new toolkit help us figure this out efficiently?
And what's really cool here is that our toolkit actually gives us 2 different paths to the answer. First, there's the long way. Using the addition rule, we can just add up the probabilities of all the passing scores, 4, 5, 6, and 7. Or we can take this shortcut, using the complement rule. The opposite of passing is, well, not passing, getting a 1, 2, or 3. We can just add those 3 probabilities together and subtract that total from 1.
And look at that. No matter which path we take, we land on the exact same answer, a 70.9% chance of passing. But let's be honest, the complement rule was definitely faster. It's all about thinking smarter, not harder.
So let's do a quick recap of the toolkit we just built. First, we have probability models, which let us map out every single possibility. Second, we have the NOT rule, our amazing shortcut for finding the opposite of an event. And third, we have the OR rule, for when we need to combine the chances of mutually exclusive events.
Look, this stuff isn't just for dice and candy and exams. It's a whole new way of looking at the world. So the final question I'm going to leave you with is this. Now that you have these tools, now that you can map out possibilities and find clever shortcuts, what are the odds you're going to start calculating in your own life?